So section 9.5 has been about parametric equations, and I myself have been having a little bit of a struggle with the whole point of section 9.5, the whole idea of parameters. It seems like there's no, it's like, where are we going with this? It's a weird little concept. It doesn't seem to fit with all the others. So I'm thinking that it's important to go ahead to 9.6 and see what 9.6 is about, and maybe we can see then how it relates. Like, maybe then 9.5 will make more sense. So 9.6 is about polar coordinates. And it says in this section, you will study a second coordinate system called the polar coordinate system. Now, the Cartesian coordinate system is what you're familiar with, also known as the rectangular coordinate system, I think. X, Y. It's named after René Descartes, who's the guy who is sometimes known for saying, "I think, therefore I am," which I think was actually not true. The thoughts inside our heads are not really who we are, but they are kind of non-stop, so it does seem almost like evidence of existence. But anyway, Cartesian coordinate system is what we're used to. X is left, right, and Y is up, down. And it's rectangular. However, the polar coordinate system is based on a point O. So let's write a polar coordinate above this. So we're making sure we're separating that from the Cartesian, different from the Cartesian coordinate system. A point O called the pole origin then has a ray coming out from it called the polar axis. And then each point P in the plane can be assigned polar coordinate r theta. So instead of going x, y, we start and we go radius and then theta. So it's how far are we from the point P origin, and then what's the angle. This should remind you of vectors. Remember how they had component form, x, y component form, and then they had trigonometric form, which was like magnitude, direction, magnitude, and then theta. So polar coordinates in that sense are very cool. Write it down. Polar coordinates are very cool. Right. I guess you should also know that r is sometimes called the directed distance, and theta is sometimes called the directed angle. And that comparison to vectors becomes important because you want to sometimes do what we did with vectors, just convert back and forth. So when we convert from polar to Cartesian, or Cartesian to polar, call it coordinate conversion, and we say that x equals r cos theta, and y equals r sine theta. And to find theta, we always say, well, tan theta equals, maybe you remember, y over x, and r squared equals x squared plus y squared. So using this, we can convert a point to, let's convert a polar coordinates to rectangular. So polar to rectangular example. We've got, we're given for
3 pi over 6. 3 pi over 6. That's just pi over 2. All right. And so we want to convert, we want to find x and y. So x equals r cos theta. Now, polar coordinates are given as r theta. So this is r, and pi over 2 is theta. And so x equals 4 times cosine pi over 2. Because 3 over 6 is just 1 over 2. You get it? All right. And anyway, pi over 2 in the unit circle, that's right here. And the cosine right there is 0, so x equals 0. Y equals 4 times 4, that's r, sine theta, sine pi over 2. So y actually equals 4. So our our xy coordinate is 0, 4. This is not any kind of normal notation. That's just me saying, or reminding you that this is rectangular, whereas this is polar. All right. Now let's go rectangular to polar examples. We'll go the other direction. Given rectangular 2, 2, what's that in polar? So we're trying to find out what's r and what's theta. Well, r is the square root of 2 squared plus 2 squared. In other words, x squared plus y squared equals r squared. So that's one of the formulas that we use for conversion. So r squared equals 2 squared plus 2 squared. So this is 4 plus 4 is 8 equals r squared. So r equals square root of 8 or 2 root 2. And theta, well, to find theta, we go tan theta equals y over x, which in this case is 1. 2 over 2 is 1. So where is the tangent? 1. We know that's true right here at pi over 4. So theta is pi over 4. And so polar coordinate is 2 root 2, comma, pi over 4. Okay, well perhaps that brings us back to 9.5 because we took a little into 9.6. We saw where we're going with this. We're talking about polar coordinates, a neutral coordinate system. But up until now we were talking about conic sections. And then we got this weird parametric equations thing. And I started this off by showing you guys that, reminding you that one conic section would be the circle, and if it has a radius 1, the equation is x squared plus y squared equals 1. But this is also the unit circle, and in the unit circle we learned this is true, and this is true. So somehow, these two parametric equations, we didn't know they were parametric equations, but in this context they are. They are two equations with a parameter. They're x and y are related to this third variable. And if we remove the third variable, we get this. But what I don't think I talked about with either class last week was how do we remove the theta from these two to get this? Where are we going to get that from? And the answer is from the place that you would think of the part of trigonometry that you least enjoy or like or remember. And if you thought of trigonometric identities, that's exactly where you find the answer to this. Luckily, there was one trigonometric identity you kind of remembered because it was thought up by the great Pythagoras, who a lot of you guys really do like. Of course, Pythagorean theorem is a squared plus b squared equals c squared. We brought into the unit circle, it's like x squared plus y squared, but then x squared is actually cosine, so we learned this cosine squared plus sine squared equals 1. And so that is where we get this. It's not through any substitution. It's through plugging each equation, the result of each equation, into this trigonometric identity. And with that. So that will help you with a problem like on your worksheet number 3, which says you're supposed to draw the equation for this trigonometric identity, these parametric equations, where x is 5 sine t and y equals 4 cosine t. And again, we know that sine squared t plus cos squared t equals 1. So if we can just get sine squared t by itself by dividing both sides by 5 and then squaring both sides. And same thing, we're going to do the same thing over here. Get the cos by itself and then square both sides. And now this becomes x squared over 25 plus y squared over 16 equals 1. And what's that shape? Well, it's an ellipse. So it's a horizontal ellipse. It's 5 wide, 4 high. Now, if you're like me at this point, you're asking, well, this is an identity, so this is this always true? This is always, let's be clear. This is always true. This is not always true. This is always true for a circle of radius 1. For a circle of radius 1. But so if you threw in a 2, that would just be a different shape, right? So this is just a different shape. It's got different parametric equations and a different total equation. Different equation with the parameter eliminated. Let's try one more. We got number 4. X equals 2 secant t. Y equals 4 tan t. All right, so secant, tan, that's going to be some version of this. That's going to be a Pythagorean version of this. If I want to turn this into something with secant and tan in it, well, the reciprocal of secant is cosine. So if I divide 1 by cosine, I'll get secant. So if I divide the whole thing by cosine, this identity becomes 1 plus sine over cosine, that's tangent. I guess I'm dividing the whole thing by cosine squared. So this becomes 1, this becomes tan squared, and this becomes secant squared. So that's how that's going to be the identity I'm going to use for this problem. Let's get secant by itself. We'll say x over 2 equals secant t. So x squared over 4 equals secant squared t. And then that comes from this. And then from this one, we got y over 4 equals tan t. So y squared over 16 equals tan squared t. And using these two, we sub into the original, sub into the identity, and we get 1 plus y squared over 16 equals x squared over 4. And then we subtract y squared over 16 from both sides. We'll just move the 1 over. This is a trick I like to do where I subtract from both sides. So then what's left on this side is 1. Oh, never mind. I'm in a weird mood today, everybody. All right. Does this make sense? I'm subtracting y squared over 16 from both sides. Slightly better view. All right, our hyperbola should look like this. x squared over 4 minus y squared over 16